Welcome. Today, we are peeling back the layers of the operating system to look at one of its most fundamental constructs, the virtual memory layout. Specifically, we'll explore the x86-64 architecture and the critical boundary between user applications and the kernel. Understanding this separation isn't just academic, it's the key to diagnosing complex system crashes, optimizing performance, and appreciating the sophisticated security mechanisms that protect modern systems. We'll delve into how this invisible map is drawn, enforced, and secured, providing insights that are crucial for any serious IT professional. Every process on a 64-bit system believes it has access to a vast 256 terabyte address space, but this isn't the full picture. The x86-64 architecture enforces what's called a canonical address form. This means only addresses where the top 16 bits are copies of the 47th bit are valid. This rule effectively splits the entire virtual address space into two large regions, a lower half for user space where your applications live, and an upper half reserved exclusively for the kernel. In between lies a massive non-canonical hole. This hardware-enforced division is the first and most important line of defense. A user process cannot physically form an address that directly touches kernel memory, ensuring system stability and security from the ground up. This isn't a suggestion from the OS, it's a law enforced by the silicon. So how does the system translate these virtual addresses into actual physical RAM locations? The magic happens in the Memory Management Unit, or MMU, which uses a multi-level page table structure. On x86-64, this is typically a 4-level hierarchy. Think of it like a cross-reference index. For every memory access, the CPU hardware walks these tables, using parts of the virtual address as an index at each level until it finds the physical address of the data. Critically, each process gets its own unique set of page tables for its user space. This is how two different applications can use the exact same virtual address, like 0x4000, yet map to completely different locations in physical RAM. This is process isolation. The kernel space mappings, however, are consistent across all processes, providing a common, privileged gateway to the system's core. Knowing the layout is one thing, securing it is another. If the kernel always loaded at the same predictable virtual address, it would become a stationary target for attackers. Once an exploit gained some control, it would know exactly where to find critical kernel functions to escalate its privileges. This is where kernel address space layout randomization, or KASLR, comes in. On every single boot, KASLR loads the kernel image, its drivers, and modules at a different, random offset within the kernel's half of the virtual address space. This simple act of randomization makes it exponentially harder for an attacker to successfully execute malicious code in the kernel. They can't rely on hard-coded addresses. While it can make low-level crash dump analysis slightly more complex, the security benefit is immense, turning a predictable target into a constantly moving one. Let's bring this all together. The strict, hardware-enforced boundary between user space and kernel space is the bedrock of a modern, stable, multitasking operating system. It's what allows a crashed application to be terminated without bringing down the entire system. The page tables are the gatekeepers of this boundary, providing each process with its own private sandbox while also creating the shared pathways needed to request kernel services through system calls. Security measures like KASLR further harden this boundary against attack. As system administrators and engineers, understanding this architecture is not optional. It informs how we troubleshoot performance bottlenecks related to context switching, how we analyze memory dumps after a blue screen, and how we appreciate the profound impact of security vulnerabilities like meltdown and